Hey, welcome back to Fat Mama Physics. In this video, I am going to walk through the tutorial that we have here for the Bohr's model of the hydrogen atom. So a lot of questions, I will probably combine a few of them together, but just to give you kind of a brief understanding of what the Bohr model is, what its features, here we go. So Bohr came along, in fact he was he a student of Rutherford? Oh, he was working with Rutherford, and he later proposed that for the model of the atom, in fact, it only much works well for hydrogen, not so much for the rest of the periodic table. We have electrons that take on specific orbits with specific energy levels, as shown here in this diagram. You have different excited states of these electrons at the different orbitals, and which these orbitals, in terms of these orbitals, have quantized amounts of angular momentum, as shown here. So MVR is angular momentum. You do not need to know how that is derived. Not part of our curriculum unless you do engineering physics. And what he means by quantized is that the particular orbits will have some integer of n times the Planck's constant and 2 pi. So where did he get all this? Where did he get this constant? It was mathematically how it worked out. There was not a lot of explanation of how and why. It was just what we found. In fact, it's just that at specific orbitals, this is some integer of the angular momentum. So that is the what he found, and it wasn't until later on when de Broglie came along. So this is before de Broglie, where Bohr just randomly found that, oh hey, there is the orbitals are related by this integer here. Then later on with de Broglie, he was able to show with the de Broglie wavelength, which is lambda is equal to Planck's constant over the momentum. Eventually, we were able to see how this all fits in. So later on in a later video, I will show how this is related. So essentially, Bohr came along and did this, and he was able to define the specific energy levels for these electrons as what we will see and show us later. So relevant to you is what's going to be in the data booklet. The data booklet, you will see this one over here, and this is essentially where we want to get to, which is the N as the energy level, and EV is the electron times the this one over here is the energy in electron volts. Okay, so let's begin with kind of Bohr's hypothesis. So Bohr's idea of the model is that you have these electrons that are in these orbits and are bound by, basically he uses the classical way to explain how this works, which is electron orbiting the nucleus, which is, if we apply circular motion to that, then we can say that these electrons stay in these specific orbits that are some distance away from the proton. So using that and total energy, in which total energy is the kinetic energy plus, well, here the potential energy is negative because due to it being attractive to the proton itself, so that when you put in a negative charge for the electron, positive for the proton, we get a negative EP, potential energy. So essentially, here is what we get. K, Q, Q, and since these are elementary charges, we just write e to the power of 2 over r, which is the separation. Okay? So what we want to do now is we kind of want to show this, ultimately. Okay? That the total energy is 1/2 Ke squared over r. Why is that the case? Well, let's get on and do this. Write out the equation for the electrostatic force equaling the net force towards the center of the circle. So essentially what this question is asking for is, imagine you have a proton, you have a proton and an electron that is orbiting this proton. Write the F net equation that describes the circular motion of the electron around the proton. So here we have m mass of the electron times the velocity, or the linear velocity of that electron squared over r, which is the distance it is from the proton it is orbiting. And this is going to be equal to the electrostatic force acting on this electron, keeping it keeping it bound by the orbit. So this is K, and then I'm going to use E for the charge of an electron, as well as for protons, the same. So E, which is just E squared over R squared. So this is it. This is what we have for the net force acting on the electron. So now that we have that, let's show that this is essentially just, let's kind of break it down, because notice that there's a few constants, some things here that can cancel out, including this, one of these r's will cancel out and go away, which leaves us with mv squared, which is mass of the electron times its velocity squared, equals to ke squared over just a singular r. Okay, now we're done that, we are going to now combine this relationship with the total energy. So this guy, we're going to combine it over here to show that the total energy is in fact just 1/2 ke squared over r. Does that look similar to something that you've seen before, maybe in gravitational potential energy of orbits, of satellites? Okay, so here we go, let's combine it. Now, the easiest way I see is just to take this mv and just substitute it in here as the other side, because mv in front, I'll have the 1/2 in front, and then mv squared, I will just put in ke squared over r. Okay, close these brackets and finish off the rest of the total energy equation. And since it is subtracting ke squared over r, or plus the minus, I'm just going to subtract it instead of adding the negative number. So now we end up with 1/2 ke squared over r minus the full ke squared over r, and if we just add them together, this is essentially just 1/2 minus 1. So this leaves us with minus 1/2 of whatever is inside, that's ke squared over r. And there you go, we've shown that the total energy is essentially 1/2 of ke squared over r. Okay, so I'm going to end this video here to show, this is the first part of this tutorial. Later on, we will combine this with Bohr's concept of the quantized angular momentum. But notice that he's using a classical way to explain the model of the hydrogen atom. So there's going to be problems that later on we will run down with, and of course problems with Bohr's model, in which we will talk about later on. So stay tuned for that. I thank you for watching. Hopefully this was helpful, and Fat Mama Physics signing out!